Hello and welcome to another episode of Classes with Atish. I was practicing integration by parts recently and I stumbled upon a process called the DI method, which I had not come across during my high school days. I found this DI method or the tabular method really interesting and very helpful in doing integration by parts. So let's talk about that a little bit in this video and I will explain how this DI method works. Okay, so let's start with what is integration by parts. Suppose we have two functions u and v, these are functions of x, okay, and we differentiate this product of uv with respect to x. So the differentiation rule says, so we will do u dv plus v du. Okay. Now let us integrate both sides. Okay. So when we integrate both sides, we can do some rearrangement and we can write u dv is equal to, this integral is actually evaluating to uv minus, we can write v du. Okay. Now let us say this function u is another function f. This derivative of v dv is g, then u is still f, v is integral g dx. Okay. This v is integral g dx and du is f dashed. Okay. Now if we write this in terms of f and g, we can write integral f g dx. So product of two functions. One function, you see f is either used as f or the first derivative of f, and the other function g, we are using the integral of g. Okay. So obviously we will choose f and g such that f is the function which is easily differentiable and g is the function that is easily integrable. Okay. So if we rewrite this, we can write this as f times integral g dx minus integral f dashed times integral g dx dx. Okay. This formula is our integration by parts formula. Okay. Now I wrote it in terms of f and g. You can also memorize this in terms of u and v. So typically in most literature you will find this as uv dx is u into integral v dx minus integral u dash times integral v dx dx. Okay. Either way you can remember it. Okay. So using this as is obviously involves a lot of steps, lot of writing, and that's where this method called DI method really is helpful. So what is this DI method? We will build a table, we will differentiate u and integrate v. Let me write this, differentiate u, integrate v. Okay. So let's first write down u and v, and then we have to write, and then we also have to write this plus minus, maybe we'll write down few times. Okay. Now u we will continuously differentiate it, u dashed, u double dashed, u triple dash, that way. Okay. There are certain rules when to stop building this table. We'll talk about those rules very shortly. Now we will continuously integrate this v dx, then let's say whatever the result is, we integrate that one more time. Whatever that result is, we integrate that one more time. Okay. It looks very complicated, but when you actually deal with real functions, it is not. Now, what is the result? If I have to integrate uv dx, and once I have built this table, what is the result? This is how we will build up the result. We will multiply this with this, making sure we take care of the sign. We'll multiply this with this with this, and so on. Wherever we stop, the last integral will be product of this. Okay. What do I mean by that? So this is 1, 2, 3. I wrote down 4 steps in the table. Let's say we have built out this table up until step 4, but let's say for some reason, depending on certain conditions, we stop at step number 2. So how we will write this? We'll write this as u times integral v dx, u times integral v dx, and since we are stopping at step number 2, the last integral will be minus integral u prime times integral v dx. Okay. Let's suppose instead of stopping at step number 2, we stop at step number 3. Then how we will evaluate this? U times integral v dx minus u prime times this plus product of this integral plus integral u double prime times dx. Okay. So this is as if we iteratively keep on building this, but when we do with real examples, you will see we really don't have to do it infinitely many times, but there are certain conditions where we can stop and quickly get at a result. Okay. But this is, I don't see this as a proof of the DI method, but this is more like an algorithm. Okay. So what I will do is, let me erase some part of the board and do some real examples with you so it makes more sense. Okay, now let's look at some examples. I will solve 3 examples to showcase you 3 patterns in which the DI method is used. So the first one will be x sin x dx. Second one we can do is e to the power x cos x dx, and third maybe we can use is x square ln x dx. Okay. Okay. So let's do the first one, x sin x dx. Okay. So the first step is to figure out which we will choose as our u function and which we will choose as v. Either choice is good in this case, but let's say x is u and sin x is v. Now let's build out the DI table. We differentiate u and we integrate v. Okay. Now, first let us write down the functions themselves, x, sin x, and then let us write down the signs. Maybe we will write down up to 3 steps. Now, we have to differentiate x. So, differentiation of x is 1. If we differentiate it one more time, it is 0. Now, we have to integrate sin x. Sin x is minus cos x, and integration of minus cos x is minus sin x. Okay. Now that we got this table, we will multiply this with this with this, and see one thing. Next time if we had integrated minus sin x, we would have got cos x, but if I multiply 0 with that, it becomes 0. So, we do not need to go beyond this step. So, as soon as, so first stop I will say is this is my stop. So, the first rule is if either this column or this column has a 0 in any of the rows, we stop there. Now, let us get back to the integration. So, this we can write as x into minus cos x. So, minus x cos x minus 1 into minus sin x. So, that will be plus sin x, and my integration is complete. So, I will write plus c. Okay. So, this is example number 1. Now, let us look at example number 2. E to the power x cos x dx. Okay. Let us choose e to the power x as my u function and cos x as my v function. Okay. Now, let us build out the table. We differentiate u and we integrate v. Let us first write down the functions themselves. E to the power x cos x plus minus plus. Okay. Now, let us differentiate e to the power x. If we differentiate e to the power x, it is still e to the power x, it is still e to the power x, and so on. But if we integrate cos x, it is sin x. Now, if we integrate sin x one more time, it is minus cos x. Let us decide to stop here. I will tell you why the reason to stop here. Now, if we rewrite this, we can write it as, before that, so we multiply e to the power x with sin x and this with this and so on. So, our result is e to the power x sin x plus minus minus plus e to the power x cos x plus, so the last row whatever we have, this will be integral of this times this. So, e to the power x times minus cos x dx. Okay. So, you can right away see what is happening here if I write another step, e to the power x sin x plus e to the power x cos x minus e to the power x cos x dx. This is the same integral that we started with. So, my rule number 2 is we stop if the product of a row is the product of the same functions that we started with. So, this is my stop in this case. Okay, we do not need to go any more beyond this. So, if this integral evaluates to I, then I can now write, so this is nothing but I. So, if I bring I to the other side, so 2I becomes e to the power x sin x plus e to the power x cos x plus c, or I becomes e to the power x by 2 sin x plus e to the power x by 2 cos x plus some other constant c1. So, that is our result. Okay? All right. I wish I had some space to do the same one by the side, but we can do it probably here. I will just demarcate this. Okay. Let us do this one here. So, the integral is x square ln x dx. Okay. Same thing, we will build out the table, we differentiate u and integrate v. Now, ln x is difficult to integrate, but it is easy to differentiate. So, this is the function that I will pick up as u, and x square we can pick up as v. Okay. So, u is ln x and v is x square plus minus plus. Okay. Now, let us differentiate ln x, it is 1 by x. If we differentiate one more time, then it is minus 1 by x square. If we integrate x square, it becomes x cube by 3. If we integrate it one more time, it becomes x4 by 12. Okay? And then we cross multiply this, and I am tempted to do this, but I will do a stop here. I do not need to go to this third step. I will tell you why. Let us just write the expanded notation of this one then, the way we learned. So, this is ln x times this. So, x cube by 3 ln x, and then if I stop here, let us just multiply these two terms and integrate. So, minus integral of 1 by x, x cube by 3 dx. Now, it becomes obvious to you why I stopped here, because if this product of these two functions is easily integratable, then we do not need to go any further, we can just stop there. So, this we can write as x cube by 3 ln x minus 1 by 3 integral x square dx, which is nothing but x cube by 3 ln x minus 1 by 3 x cube by 3 plus c. Okay. Or we can simply simplify this as x cube by 9. So, these are the three simple rules that I have figured out so far, where to stop while building this DI table, but this is a very, very useful way or a useful algorithm how we can do integration by parts, and this method I learned is called DI method. Okay. So, feel free to leave some comments and let me know if you like the DI method. I found it pretty useful, and going forward I am definitely going to use the DI method whenever I come across integration by parts. Cheers.